In previous videos, we have looked at ionic bonds in which there is a transfer of electrons from one of the atoms that becomes positively charged, the cation, to another atom or group of atoms that become negatively charged, and we call that an anion. So that's an electron transfer. We also look briefly at metallic bond, and that's what you get between different atoms of metal. And in that case, what you have is a pooling of electrons. So the electrons from the outer shells of the different atoms of the metal pool together, and those electrons become delocalized. They don't belong to any specific atom of the metal. They belong to all of them. They are shared across all the atoms. And they are kept together by the electrostatic interaction of those positively charged atoms, which they haven't lost the electron, they just kind of are sharing it with others, and the sea of electrons. And the last type of bond we're going to be looking at, which is hugely important because most of the atoms will make this type of bond, is covalent bonds. And covalent bonds typically are formed between non-metals. And that's what we will be covering in the next few slides. Before we charge ahead and we look at what a covalent bond is, we need to look back slightly at how atoms make bonds, so when they make one type of bond and not the other. So this counting metallic bond, which is made among metal atoms, we've got a sort of tension between will my atoms make a covalent bond, or will they make an ionic bond? And to answer that, we need to look at two key variables, which are actually periodic table properties. They periodic trends. You know how an atom is going to behave roughly depending on its position in the periodic table. One of them is ionization energy, and the other one electronic affinity. So ionization energy is the energy you have to spend in taking an electron away from an atom, so it becomes positively charged. And electronic affinity is the energy release when an atom gains an electron and becomes negatively charged, and it's defined one at a time. And if you look at the values I've got in the slide, we've got sodium. That is very easy for sodium to lose an electron, or to take an electron away from an atom of sodium. That value, 469 kilojoules per mole, is a positive value. It means that it's energy that we are going to have to spend, but it's not a large number, and I will show you what I mean with not large compared with what I consider large. And then you have an atom like chlorine that will release quite a lot of energy when it gains one electron and becomes negatively charged, a chloride anion. And I've got here minus 348 kilojoules per mole, and the minus means it's energy liberated. So if you have elements with low ionization energies, which find it easier to become positively charged, and that's a typical example for metals, and you have elements that find it easy to become negatively charged and typically are non-metals, and you have both of them together, then what you form is an ionic bond. There is an exchange of electrons. One finds it easier to lose an electron, the other one finds it easy and very favorable to become to gain an electron. So that's a perfect pairing for an ionic bond. But in many cases, things don't work that well. In many cases, the ionization energy is a little bit too high, so it's not that easy for something to become positively charged, and the amount of energy liberated by the other atom become negatively charged is not that great either. So what happens when those atoms find each other? Does it mean that they don't make bonds? Or no, the answer is no, they do make bonds. They just make a different type of bond. Let's see here the example of carbon and chlorine. Carbon, as you can see, in terms of ionization energy, has quite a large ionization energy, 1000 kilojoules. If you compare with the 400 and something that I was showing you before for the sodium, that's a lot of, it's like almost 3 times, 2.5, 3 times the amount of energy it would take you if that, instead of being carbon, that was sodium. So carbon is not going to particularly like to become positively charged. On the other hand, you can think, okay, well, it could become negatively charged and become a negative anion. However, if you look at the value, minus 153.9, again, it's 3 times less than if you had, for example, it's around half of what you would have if you had another atom that would find it much easier, for example, chlorine. So carbon is not an atom that particularly likes to become positively charged or negatively charged, because the energy that is required to make it positive and energy liberated to make it negative is just not worth it. And then you have an atom like chlorine. So yes, chlorine finds it excellent to become negatively charged, gain an ion. If you look at this electronic affinity, it's roughly double, a bit over twice the amount that the energy you would get if that was carbon. And it doesn't like at all to become positively charged. Look at how losing an electron, you will need to spend 1,251 kilojoules per mole of chlorine to take an electron away from the chlorine. So what happens when you have carbon and chlorine together? Do they not make a bond? Do they just think, okay, well, yes, you could accept an electron from me, but I'm finding it difficult to release it, or you cannot give me an electron, and even if you could, actually, I'm not that good at accepting it. Do they not make bonds? Yes, they do. They just don't do them by losing or gaining electrons. Energetically, it's not worth it. So what they do is they share their electrons, forming covalent bonds. So there's no exchange of electrons. There's no one becomes positive, one becomes negative. There is a sharing of electrons. And we signify that sharing of electrons by putting a line between these two atoms. And I can vouch for carbon and chlorine. They make a perfectly stable compound. It's called carbon tetrachloride, in which four chlorine atoms make bonds, covalent bonds, with carbon. So yes, they make bonds, they just don't make ionic bonds. They make covalent bonds. The next couple of slides are perhaps a little bit beyond the scope of this module, but I thought it would be useful to give you some sort of mental image of how these sharing of electrons might look like. And I've picked a couple of quite simple molecules. The molecule of hydrogen, and in the next slide you will see the molecule of chlorine. Look at how I use the word molecule. Yes, they are compounds, they're all compounds, but apart from that, when you have covalent bonds, you can properly talk about molecules. More about that in a future slide. So you've got here the two atoms of hydrogen, and hydrogen has only one electron. An electron is in a 1s orbital, so it's quite close to the nucleus, and in an orbital s, it's sort of a spheric shape. So when you have the two atoms of hydrogen and they are close enough together, then those two orbitals will overlap, and you will have a different orbital form by the overlapping of these two hydrogen orbitals, which before and that will mean that the electrons are shared. Before, each electron belongs specifically to one of the hydrogens. When the atoms of hydrogen are close enough together that those orbitals can interact, then you have a different electronic density. And this shared pair of electrons will spend most of the time in the middle of the two atoms, attracted by the two nuclei of the two hydrogens. This is an example of how this covalent bonding looks like, or could look like, when you make a molecule of chlorine, what we call diatomic chlorine, or Cl2. So not the atom chlorine, but the compound chlorine, which is two atoms of chlorine bonded together. In this case, the electrons that those two chlorine atoms are going to use are p orbitals. That's the highest, is the highest energy level occupied, and the emptier, the unoccupied orbital that has one electron. It could have up to two. And if you look at the first image on the left, that's signifying the two p orbitals from each chlorine atom. If you think of the chlorine atom here in the middle, separated. When they get closer enough together, then there will be an overlap of those p orbitals, and then they will form a different orbital. So the bond forms. we call it a pair orbital because you have made it by pairing two orbitals, in this case a pair p orbital. And then you will have the chlorine atoms and the two electrons that will spend most of their time, the area of the region which is more likely to find it is in the middle, in between those two chlorine nuclei. And those of you that might be familiar with the octet rule and how the electronic shells being as complete as possible, trying to imitate the structure of the noble gas, this might sound familiar. If it doesn't matter. This is not the purpose of this module. It's just that you have this awareness that just because two atoms cannot exchange electrons, that's perfectly fine. Most atoms will not exchange electrons, they will share them, and that's how they will make their bonds.